Hello and welcome everyone. I'm a first-year PhD student here at the Eötvös Loránd University. My supervisor is Daniel Berényi from the GPU lab of the Wigner Research Center, and Tamás Kozsik, who you've met at the opening ceremony. And together we are studying high-performance computing from a high-level functional perspective. First, I will talk about our recent experiments about data locality and predicting runtime performance. But before that, please let me briefly sketch our motivation for this research and the main milestones of our previous work. So, as you know, there are scientists who are working with large multidimensional data sets, and they are combining those using some kind of formulas described as mathematical equations. They want those computations to be as fast as possible, but they are usually not experienced or not even interested in low-level optimization. And there is a lot to be experienced in. So, as you have also seen, mapping a hierarchical computation to a hardware hierarchy is far from being trivial. And that's where we come into the picture. We are working on a tool, it's called LambdaGen, and it aims to automate this process of mapping computation to hardware with close to optimal performance, while requiring as little input from the user as possible. And how does the functional approach come into? Well, if the computation is already described as mathematical formulas, then why would we lower them to loops when functional primitives are much easier to handle and optimize? So we have this compiler. Its input is an expression tree which has quite few nodes, which makes implementation and optimization way easier. Most of them is simple. We have this data view that is basically just a pointer with static size and stride information, and this redo zip, which is just the fused mapping and reduction. For example, you can describe a scalar, a dot product with two vectors, a function that zips them together, and then a function that sums the result. Okay, so the expression tree comes in, and the compiler performs a series of passes on the expression tree. Each pass places some annotations on the tree nodes. One interesting point is that all compiler passes are implemented as recursion schemes, which make them well composable and may be optimizable, although that's a future research direction. We also implemented pattern-based search trails, also using recursion schemes. So that's how we actually make modifications to the expression tree. For further details, you can check out our talks in the last 2 years of GPU days. Okay, so let's see how we, why and how we would want to make changes in expression trees or computations. On the left side, you see, on both sides, you see a matrix vector multiplication. On the left side, it's performed by computing this scalar, the dot product of each row of the matrix with the given vector. It's expressed as a redo zip operation nested inside a zip. And on the right side, it's the same computation, but formulated as computing the element-wise products of the elements of the vector with the columns of the matrix, and then summing up the columns. The result is, of course, the same, But the runtime performance can be quite different, because the left side you can trivially parallelize to 3 threads, but you only need to take 1 scalar in cache, in memory. The right side you can parallelize to 4 threads, but you need 3 values in memory. Of course, you can imagine how it goes for larger sizes. And in the expressions, you can see that the zip and the redo zip operations were swapped, and the addition was lifted to the level of vectors using a zip. So this kind of operation swapping can be generally found using a pattern tree like this. And if we provide a replacement tree like this, then we can automatically find and apply this change in the expression tree. And we can also do similar changes in the tree by subdividing the operations and subdividing the data logically, the data layout. And combining these 2 operations, the swapping and the subdividing, we can create a whole lot of equivalent operations which may have quite different runtime performance. The details of this work are in our previous publication. So how does this really affect runtime performance? We've experimented with the matrix multiplication. It's 2 outer loops basically and the scalar product. You can see this row is how you would probably code it naively or first approach. And we have applied the reordering operation to generate all possible orderings, and found that the optimal one is 10 times faster than what the user would probably write. The only problem is with this approach is that we have to compile and benchmark or n factorial orderings, where n is the number of operations. But one other thing is that if we subdivide any of the operations, we get even more possible reorderings, and among those there will be even faster ones than this. So how to avoid compiling and benchmarking so many probable computations? Our goal was in these past months to somehow predict how fast each of those versions will run. But first we didn't want to work with all the expressive power of the lambda-GAN language, so we just focused on tensor contractions. They are very simple computations with some probably nested summations where the operands are other summations or tensors. We used the server CPU, and I used the Google benchmark library, which I was quite satisfied. Okay, so we generated random tensor contractions where we constrained the number of sum nodes and tensor nodes. And we've also generated specifically modified matrix multiplications where we transposed 1 or 2 of the operands, and we've generalized a bit, added more dimensions. So these matrix multiplication kind of expressions. Altogether we had 92K measurements, and more than half of them was with just 1 sum, so they're really simple ones. Okay, how would someone start predicting runtime performance? Well, an intuitive approach is that what takes time? Performing operations like arithmetic operations and loads and stores. So why not we count how many of those we will perform, and each will take some time, add those together, and that's our running time. Of course, linear regression is a suitable way to find the coefficients. So that's what we did for all our one-sum benchmarks. So only the simple ones. The result is not so satisfying. The average error was quite high, though the average error is not really meaningful for us because a few measurements with very high error can pull up the average error. So we've computed another metrics which is the full width at half maximum. So the width of this histogram at the maximum of the highest peak. And also we've counted how many measurements were predicted well enough. What causes the linear regression to perform so it underperformed? Obviously, there are some nonlinear effects affecting the runtime. Otherwise, the linear regression would be perfect. Let's see some concrete examples where the linear regression failed. Here are two summations. We basically sum up the rows or the columns of the A matrix. The difference is only the size of the second dimension of A, and it decreased by 3. How much would that change the runtime? Well, we didn't expect much difference, but actually the difference is 10 times slower if we decrease the size of A. At first I thought this must be some kind of noise or measurement error or something, but believe me, these two measurements are absolutely reproducible on that specific CPU and the compiler we used, which is GCC7. So there are some things, obviously, that don't fit into our linear model. And it is related to data locality. So as you've heard multiple times today, using the different levels of cache is very important, also on a GPU, but even on a single core, single threaded CPU application. We have multiple layers of cache, and the load operation time actually depends on which cache the data we are reading from. And unfortunately, on a CPU program, we have absolutely no way to instruct the compiler or the CPU in which cache to put our data. So we have to make guesses what will happen at runtime. Let's see what can happen. A typical CPU loads a full cache line of elements at each read operation. So if I request one element from memory, it will actually load the appropriate cache line from the memory and put it in the cache. Where it puts in the cache depends somehow on the address of the given element in memory. And how exactly it depends is, well, kind of a black box. It could probably be investigated, but for right now, I would rather not. I would be happier if my model somehow implicitly contained that information. Okay, so it reads the element, puts it in the cache. So if in the next iterations of my code I access those elements, then those reads are basically free because I'm guaranteed to load them from cache. But if I'm not reading those elements in the next iterations, but somewhat later, some outer loop has to go around, and then do I return to those neighboring elements, then it depends whether it will be still in a cache. What does it depend on? Well, the cache size and the loop ranges together, so whether I've read too many other elements or not. And of course the cache policy, which is another big black box, because how it will decide which elements should it keep in cache. Well, maybe it uses some least recently used policy or something completely different. And as a last source of unpredictability, that is the prefetching, which complicates things a lot. So this makes it pretty clear that no kind of linear model will ever work. So our next guess was to try to build some kind of neural network and hope for the best. So maybe it will grasp at least some of these sources of unpredictability and provides us better results. Before that, let's see some of these effects in action. So what we did here is benchmarking these two expressions. One reads, the A matrix is always stored column-wise, and once we're reading it, stored row-wise, so standard C memory layout, and once we're reading it row-wise, so that's a regular access pattern, and next time we are reading it column-wise. The row-wise version is very simple. Okay, so I should also say what the axes are. So we fixed the product of these two dimensions to be a million, and changed the ratio of the extents. So first I starts increasing to 1,000, and then J starts to decrease. Yeah, and then we can see that the runtime of the first version, which reads row-wise, doesn't change at all while changing the shape. So that's just what we expected, because we always reach elements one by one. We always read from cache, and nothing bad happens. But if we read column-wise, then things start to look a bit crazier. The very first one is the same as the row-wise read, because you just jump two elements forward and then one back, and two forward and one back. So basically you are still always reading from cache. But as we increase the size of the rows, then the runtime starts increasing, and then at one point it stops increasing, and then in the end it just goes crazy, and it seems like multiple data locality effects are in action. And that's still not noise. We still repeated the benchmark multiple times and get the same results. As a quick bonus, you can see the effect of how pinning threads to cores affects the noisiness of the measurements. Okay, so we wanted to create a neural network which is easy for number vectors, but how do we map an expression tree to a vector of numbers, so some kind of state vector? We came up with a following process. We embed the indexing of the tensor to this state vector field using an embedding matrix, and also the size of these dimensions. And then at these summations, we combine the state vectors coming from the operands and combine to that state vector the range of the summation and the index of the summation. So a sketch of the structure of our neural network is here. The blue boxes are the parameters that the linear network can learn, the neural network can learn. We have these linear transformations, these ones and here that align the state vectors to be in a composite, in a structured space. And one additional specialty of this network is that we try to handle the multiplicative effects and the additive effects of the runtime separately. So it behaved way better than the linear regression. The average error was smaller. This width was way smaller, and we also got more acceptable predictions. Well, that's it. So it seems that that the neural networks can grasp some of these nonlinear effects of data locality, but well, there is a long way to go. So this was just scratching the surface. We will evaluate how representative our generated expressions were. It's not clear whether we should over-represent some of those tricky cases for the neural network to learn them better. We could also use the neural network a bit differently, like now we predicted the runtime, and for the optimization it would be enough to predict whether one version would be faster than the other, and maybe that's an easier thing to answer with a network. And we should probably also try to open some of those black boxes, so we can see whether we can model them directly without too much hacking. Yeah, so thanks for your time and your attention. We are also thankful for Robert Csordás and Gábor Lehel for valuable discussions, and if you are interested in how our project goes, please check out our GitHub repository. Thank you.
Thank you, András. Time for questions. I can see you guys maybe for coffee, but I have a question.
There is one.
Okay, please.
So you were talking about those different black boxes you maybe want to open in the future. What is the first one you want to open?
What is the first one? Well, good question. I'm particularly interested in that graph I showed you with the crazy up and down movement of the runtime. So I would particularly be interested in explaining which effects cause that from the black boxes I listed or some other black box I'm not. I do not know. So that would be the first.
Fantastic.
Further questions or remarks? Okay, so mine was related to this one also, so you asked my question. So, okay, if there's no further thing, then we can still continue the things outside during the coffee break, but I really ask the speakers of the next session to come down, and let's thank András again.
Thank you.